In this video, we will talk about moment of inertia. We will present more details on moment of inertia that we did not discuss in our previous video. We will look at moment of inertia for systems such as uniform rods, uniform solid cylinders, spheres, and so on. We will also discuss the so-called parallel axis theorem that relates moment of inertia of a body about an axis through the center of mass of the body to the moment of inertia about an axis that is parallel to the axis that goes through the center of mass. In addition to kinetic energy calculations, moment of inertia also plays a significant role in the calculation of so-called torque and angular momentum of a body, as we shall see in the future. Finally, we will solve problems associated with the concepts presented. As we have briefly mentioned in our previous video, moment of inertia is a rotational analog of mass. It depends on two things. It depends on the mass of the body and also the position of the rotation axis. So if we change the rotation axis, the value of the moment of inertia will also change. In this respect, it is fundamentally different from the mass of an object, which is a constant. Let's look at our first system, a dumbbell-like system. You have a couple of masses. Let's call the value of the mass m on the left and m on the right in kilograms respectively. The blue line, the dotted blue line, is the axis of rotation. Let's say both the masses are situated at a distance r from the axis of rotation. As we have seen in our previous video, the moment of inertia for such a simple system is given by the sum of individual moment of inertias. So in this case, the mass on the left, the moment of inertia with respect to the rotation axis, is the mass times the distance from the rotation axis squared, plus another term for the mass on the right, mass times the distance from the rotation axis squared, so you get 2mr squared. Now we note and we stress that such a calculation holds only for point masses, such as for this dumbbell system. For a uniform rod, such as the one shown, the one with mass m and the length L, and the rotation axis is in the middle going through the center of mass. So when we say a uniform rod, we are referring to a rod whose center of mass lies exactly in the middle, and the mass is distributed uniformly throughout the rod. For such a rod, the moment of inertia through such an axis through the center of mass, is given by 1/12 times mass times the square of the length. Now, as you can see, the unit is kg meter squared. Now for a sphere, the moment of inertia of a sphere about an axis that is going through the center, the mass of the sphere being m and the radius of the sphere being r, depends on the fact that if the sphere is a hollow one or a solid one. If the sphere is a hollow one, the moment of inertia through such an axis is given by 2/3 mass radius squared. And if the sphere is a solid one, then the moment of inertia through the center of mass is given by 2/5 mass square of the radius. And again, from the expressions, you can see the unit of center of mass is kg meters squared. What about a solid uniform cylinder, such as the one shown? This is the axis of rotation. The center of mass is somewhere there, so the axis is passing through the center of mass. The moment of inertia, in this case, will be half times the mass times the square of the radius of that solid uniform cylinder. And again, you can see the unit is kg meter squared. Next, let's look at parallel axis theorem. Now, we have mentioned before that the position of an axis of rotation is important in determining the value of moment of inertia, and this theorem is associated with that observation. It states, if I sub cm is moment of inertia of a body about axis through the center of mass, then the moment of inertia I of that same body about a parallel axis situated at distance r meter away from that center of mass axis is given by this expression. So the new value for the moment of inertia is given by the moment of inertia of that system about an axis that passes through the center of mass, plus a term that is dependent on the square of the distance between these two axes. And of course, an important condition for this theorem to work is that these two axes must be parallel to each other. To highlight how the parallel axis theorem works, let's look at this very simple example. This is the dumbbell system that we have seen before. Let's first calculate the moment of inertia about that axis. So this axis goes through the center of mass. So ICM, moment of inertia about an axis passing through the center of mass, is given by the mass times the square of the distance for the first mass, plus again the mass on the right times the square of the distance for that mass, and that's going to give you 4 kg meters squared. Now we want to determine the moment of inertia of the same system about that axis, an axis passing through the 2 kg mass on the right. As you can see, this axis and that axis are parallel to each other, and they are displaced a distance of 1 meter. So parallel axis theorem should work. So let's call the moment of inertia about that axis I. So I is given by ICM, which we have computed above, 4, plus a term that is dependent on the square of the distance between these two axes. So the mass of the system is 4, 2 plus 2, so that's 4. The square of the distance between the two axes is 1 squared, which then gives you 8 kg meters squared, 4 plus 4. Let's apply the parallel axis theorem to uniform rod. Now we have seen that the moment of inertia for such a rod about an axis passing through the center of mass is given by 1/12 times mass times the length squared. So what about the moment of inertia of the same rod about such an axis, which is situated on the left-hand side of the rod and parallel to the first axis through the center of mass? So the new moment of inertia I is given by the moment of inertia about the axis through the center of mass, which is that, plus the term that is dependent on the distance between the two axes, which is L/2. So the mass of the entire rod times L/2 squared. So since we know the first term is 1/12 ml squared, substituting that in here, we can calculate I to be 1/3 mass of the rod times the square of the length of the rod. Let's look at a problem. Calculate the moment of inertia of a uniform rod with mass 0.5 kg and a length of 1 meter about an axis perpendicular to the rod and located at a distance 22 centimeters from the left end. So since this is a uniform rod, the center of mass is right there at a 0.5 meter mark. So this is the axis through the center of mass. So the left hand side is 0.5 meter and the right hand side is 0.5 meter. So those are two distances from the two edges. First, let's calculate the moment of inertia about that axis. So that is the moment of inertia about an axis through the center of mass. For such a rod, it's given by 1/12 times the mass, which is 0.5 kg, times the length, which is 1, square that. What we are interested in is to determine the moment of inertia about this blue axis, which is situated at a distance of 28 centimeters from the first axis that goes through the center of mass. How we know it's 28 centimeters? We are told that the new axis is located at distance 22 centimeters from the left end. So this must be 28 because the sum has to be 50 centimeters. So the new moment of inertia about this axis, let's call it I. It's given by the moment of inertia about the axis through the center of mass, which we have computed here, plus the term that depends on this distance of 28 centimeters. So the mass of the entire rod is 0.5 times the square of that 28 cm distance converted into meter. So squared. And that's going to give you, which will give you 0.081 kg meter squared. Problem 2. So you have a rotating wheel in the form of a solid uniform cylinder. Mass is 400 kg, radius is 0.8, spinning about its axis. So if you have a cylinder like that, the axis is that way, and of course it's going through the center of mass. Now if its angular speed is 60 radian per second, calculate its kinetic energy of rotation. So we have to calculate the moment of inertia first for such a cylinder, and then we can use it to do the kinetic energy of rotation. We know the moment of inertia for such a cylinder through the center of mass is given by 1/2 times the mass, which is 400 kg, times the square of the radius, 0.8 squared, which is 128 kg meter squared. Now we can determine the kinetic energy of rotation from the formula half times I omega squared, which we have seen in our previous video. So moment of inertia is 128, omega is 60, so the square of that, and that will give you 2.3 times 10 to the power of 5 joules. This is just to illustrate the importance of center of mass in kinetic energy calculations. Problem 3. So you have a thin uniform solid slab. Mass is 0.2 kg. The edge lengths of 4 cm and 8 cm respectively. What is the moment of inertia about an axis through one corner and perpendicular to the plane of the slab? So this is the plane of the slab. This is the axis through the center of mass, and this is the new axis about which we want to determine the new moment of inertia. The moment of inertia about the axis through the center of mass, that one that's going through the center of that slab, is given by 1/12 times the mass times the sum of the square of the two sides. So this could be A, this could be B. So substituting for mass A and B, you will get mass is 0.2, A is 0.08, converted to meter that is, plus B is 0.04 squared. That's going to give you 1.333 times 10 to the power minus 4 kg squared meter. So that is the moment of inertia about the axis through the center of mass. We want to determine the moment of inertia about this axis. So first we need to know what that distance between the two axes is. Let's call it R. Viewing from the top, that distance is just the hypotenuse of that following triangle. So this is 8 divided by 2, which is 4 cm. This is 4 divided by 2, which is 2 cm. And that is R. And you can determine R from Pythagoras theorem, which will give you 0.045 meter. Now using the parallel axis theorem, the moment of inertia about the new axis is given by I about the center of mass axis, plus the mass, which is 0.2, times R squared, where R is what we have computed below, and that's going to give you 5.3 times 10 to the power minus 4 kg squared meter. And that solves the problem. Thanks for watching.